alternating series, and absolute and conditional convergence. An alternating series is a series whose terms are alternating positive and negative. So they're either going to be of the form minus 1 to the k times a sub k, or minus 1 to the k plus 1 times a sub k, where your a sub k's are positive. The following theorem is the key result on convergence of alternating series. It's called the alternating series test, and it says that an alternating series converges if the following two conditions are satisfied. The first is that your terms are decreasing, or shall we say non-increasing, because they could be equal, and that the limit of your terms is headed towards 0. So for example, the alternating harmonic series, which is the harmonic series being multiplied by -1 raised to a power, has that our a sub k's are equal to 1 over k, and that's definitely a decreasing sequence, and we know that the limit of our a sub k's is equal to 0. So by the alternating series test, we know that the alternating harmonic series converges. Alright, let's look at another example. I want to know, does this series converge or diverge? So the requirements of the alternating series test are going to be satisfied because we'll let our a sub k's be equal to this. They're clearly positive. And if we compare the kth term to the k plus first term, well, to show that this inequality holds, then what we're going to show is that the ratio of the k plus first term over our kth term is going to be less than 1. To do that, here's the ratio of the terms. We go ahead and simplify this out. And when we do that, we get this. Now, clearly, that's going to be less than 1, because if I take the denominator here and rewrite it as k squared plus 4k plus k, then here's this k squared plus 4k here and here. So the denominator is definitely bigger than the numerator, so my whole thing is going to be less than 1. Alright. So, since I have that my terms are decreasing, I can also show that my limit of my a sub k's is equal to 0, and that's just because it's a rational function in terms of k, and the degree of the denominator is greater than the degree of the numerator. So by the alternating series test, the series converges. Sometimes we don't care about the actual value of the series, we care whether it converges or diverges, and sometimes we just want to know, is it approximately equal to something? Well, there's something called the alternating series estimation theorem, and here's what it tells us. It says if we have an alternating series that satisfies the hypotheses of the alternating series test, so the terms are non-increasing and the limit of the terms goes to 0, and if the sum of the series is approximated by the nth partial sum, s sub n, then the absolute value of the error, meaning the difference between s and s sub n, that error is going to be less than our n plus first term, or the first unused term. Furthermore, that sum that we found is going to be between our nth term and our n plus first term, and the remainder has the same sign as the first unused term. Alright, so just writing out what that says again, it's telling us that the sum of the whole series is approximately equal to the sum of the first n terms of the series. And that if we want to know how far away that error is, you know that the absolute value of the error is going to be less than your n plus first term of the series. This right here is what we call the error. This is your first unused term. And furthermore, it told us that the sum s is going to be between our nth term and our n plus first term, and that this difference, s minus s sub n, is going to be positive if our n plus first term is positive, and it will be negative if our n plus first term is negative. Alright, so let's use this. How many terms should be used to estimate the value of this series with an error of less than 1/1000th? And here there's a typo. That infinity right here should be on top of my sigma sign. So here we go. In order to do this, what we need to do is we need to find the n such that our n plus first term is going to be less than 1/1000th. Alright, so here's our n plus first term, and we want that to be less than 1/1000th. So solving this equation for n, I flip it. When you flip it, you have to change the direction of your sign. I subtract 3 from both sides of the inequality. Since these are all positive numbers, I can just go ahead and take the square root of each side of the inequality, and then to get n alone, I'll subtract 1 from each side, and I get that n is going to be greater than 30.575. So that means when I choose my n, I should choose n equals 31. That means I need 31 or more terms in order to get a good approximation.